So I'm going to be going over 427 through 429. So on page 427, nothing is really important. These three sections aren't really important. It's just that red giants are 100 times greater than the sun, supergiants are 10 to the 6 times greater than the sun, and white dwarfs aren't able to find its luminosity because of its size. Two things that are important are variable stars, which they have changing luminosity because of their change in size. So as it gets bigger, its luminosity increases. So this causes a cycle known as the Cepheid cycle variable. And these stars give the HR diagram a instability strip here. And if we're given the temperature of the star and its luminosity class, we're able to find its location on the HR diagram, and we can find its luminosity. Once luminosity is found, we can calculate the distance from the star, from Earth. So it's shown in this worked out example. Maximum wavelength of a distant star is measured to be 600 nanometers, and its apparent brightness is 1.0 times 10 to the negative 12 watts per square meter. What is the distance from the Earth? So we use Wien's law to find the star's temperature. Maximum wavelength is equal to 2.90 times 10 to the negative third over temperature. And then we have to find temperature, so they rearrange it so that 2.90 times 10 to the negative third over 600 nanometers is equal to 4,800 Kelvin. And then if we look at that, apparently they just approximate it to the sun because it's in this class. Let's see, it would be like right around here. So it's class K. But I guess it's going to be the luminosity of that of the sun. So the sun's luminosity is 3.84 times 10 to the 26 watts. And using apparent brightness of the star, it's related to luminosity with the equation B, apparent brightness, is equal to luminosity over 4 pi distance squared. So they rearrange it to find distance, so that distance is equal to the square root of luminosity over 4 pi b squared, or b, which is apparent brightness, and then that will equate to 5.5 times 10 to the 18 meters, which is around 584 light years. So for 14, we just basically do the same process as what they did in this worked out example, and we can do it right now. So 14A, maximum wavelength is equal to 2.9 times 10 to the negative 3 over temperature. And this is Wien's law, Wien's law. And we have to find temperature, so we just rearrange it. And they also give us maximum wavelength. So temperature would be equal to 2.9 times 10 to the negative 3 over the wavelength, which is 400 nanometers. So 400 times 10 to the negative 9. And then we get temperature is equal to 7,250 Kelvin. Excuse me. And moving on, if we look at the HR diagram, it's based on its temperature. We can tell that it's around right here. And because they approximate it to 3.84 times 10 to the 26 in the last equation, I'm just going to do that here because, excuse me, they basically do that for the previous equation, and it's within these classes here. So we can calculate, so the luminosity would be that of the sun, and now that we have its luminosity, we can calculate the distance from Earth. So we just use the equation D equals the square root of luminosity over 4 pi times B, which is its apparent brightness, and because we already found luminosity, we already found luminosity and apparent brightness, we can solve for distance. So it's equal to 3.84 times 10 to the 26 over 4 pi times its apparent brightness, which is given 0.5 times 10 to the negative 12. And then this will eventually equal 7.8 times 10 to the 18 meters. Excuse me. So for question 15, I didn't really understand it because they give us the class and the apparent brightness. So I suppose that we're able to find these, but it's not really told in this section. So except for luminosity, temperature, and distance from the Earth, I didn't know how to find radius. So I just had to do some research, and I found out that its radius was 2 times the radius of the sun. So its luminosity is, because of its apparent brightness, is 6.5 times 10 to the negative 10 watts per square meter. It's around, and its class is A, so A class. It's going to be this value, or not this value, well, right above this value. So it'll be 10 times the luminosity of the sun. So part A is 10 times the luminosity of the sun. Radius, I had to do some research, and its radius is around 2 times that of the radius of the sun. And temperature, I also had to do some research because they only give us this amount of information. So it's around 8,000 Kelvin. And then we can use the distance formula, which is D equals the square root of L over 4 pi times B, which is apparent brightness, and L is luminosity. So because luminosity is 10 times that of the sun, it would just be 10 times the 3.84 times 10 to the 26 over 4 pi, and they give us apparent brightness, which is 6 times 10 to the negative 10. Was it 6? It was 6.5. Just I don't have space, so 6.5 here, and then it'll equate out. Let me see my notes. 6.86 times 10 to the 17 meters, and this is the distance from the sun. This is the distance from, not the sun, distance from the earth. So, mass luminosity relationship. So this just explains that some stars that we see could be a binary star systems, so that they're actually two stars, and this leads us to that luminosity is equal to mass times to the 3.5 power for the sun, dividing, and then this is the sun's notation. So remember this circle with the dot. The subscript circle with the dot just means relative to the sun, and then it gives us this relationship, that mass over mass of the sun all to the 3.5 power. So if we know the luminosity, we can find the mass of the sun. So using the information, estimate the ratio of the mass beta pictoris to the mass of the sun. So we just use that equation or ratio they give us. So L over L of the sun is equal to M over M of the sun, all to the 3.5 power. And because they said that luminosity was 10 times that of the sun, it would equal 10 for this case. They're using the star that we analyzed for question 15. So, given that we solve for the mass of the star, so we don't really need this information here. And so if we solve for m, m over m of the sun is equal to 10 to the 1 over 3.5 power, because we have to isolate m. Then we multiply by m of the sun. So m would be 10 to the 3.5 times the mass of the sun.